Okay. Yeah. Okay. Yeah. It's now it starts recording. Okay. So welcome to today's class, and yeah, have any questions so far? Uh, so anyway, just we started the introduction in the last two lectures and all. So today mostly we'll try to complete or finish that introduction, and tomorrow we'll start the instruction set. So yeah, before going to the lecture, I just want to mention that I have approved most of your requests, and I can see that now the roll list contains about 239 entries. That is 239 students can be seen right now. And still I have approved, but some of their names were not still showing in the roll list. So I just want to just show that whose names were not appeared in the roll list, but still I have approved. So please uh, like check with your the faculty advisors. Hello. Yeah. So yeah. So what you can you see the Excel sheet? Hello.
Yes, sir.
Yes,
Hello.
yes, sir.
Okay, good. Yeah, right. Okay. So I just want to mention these are the 239 names. Anyway, all your names were there in the roll list, most of your names. But what I want to mention was actually these names. They are the names over here. I just mentioned in the Excel sheet. So these names I have approved, but their names are not there in the roll list. Maybe that the faculty advisors have not approved. I don't know what is the reason and all. So please check with the concerned people and see that your names will be there in the roll list and all. Or otherwise, if you are anyway, if you are not interested, that's also fine. You can able to withdraw or anyway, because 11th is the last date for the course registration that was extended from 8th to 11th and all. So I hope that by tomorrow or by this week, the roll list will get stabilized and all. So yeah, please, yeah, these are the list of the names that are not reflecting in my roll list. There are about 45 names were there, which I have given approval, but their names were not showing in the ERP. So yeah, please take care of that. Okay. Then yeah, then coming to the continuation of the the lecture. So yeah, before going to that, I just want to mention that yeah, right. So yeah, now you can see that the class strength is roughly around 240, right now 239, and it may go around maybe another maximum another 10 people may join in the roll list and all. I hope so. So it will be around 250. So so I will what I thought was actually I have 10 TAs were there, teaching assistants. So I divided them into the two groups, like five, and then the five of the TS and also they will focus on the computer architecture part. That means if you have any queries or during the midsem evaluation and also those five group of TAs, so they will be help. They will assist you. They will assist my course and all for clearing your doubts, or if you have any queries and also please be in touch with those five people regarding computer architecture and all. And likewise, there is another five TAs which the same way they help you in the operating systems part and all. So that I will just in the end of this week, I hope that the role list will get stabilized. Then after that, I will split that entire class strength into five groups. And then I will mention that the two people, the pair of TAs who will assist you of a particular group. And suppose a group one and all, So there will be two TAs will be there will be two TAs will be assigned. One TA will be taking care of architecture part, and other TA will be taking care of the OS part and all. So that way, the total class strength will be divided, split into 5 groups, and then each group will be allocated two TAs, and the TAs will be like they will take one TA will take care of architecture part, and other TA will be taking care of the operating systems part. So this way we'll manage the class later on. And this weekend, most probably, I will split the class strength into 5 groups, and then I will assign the TAs for each group, the two TAs, one assist you for architecture, one assisting you for operating systems. So this is the way we'll go ahead with the class of this huge strength and all. Okay. Uh, so so this now let us start the class, and then let us complete this introduction part. This is mostly, as I mentioned, this is a very introductory thing, and it's most of you are familiar with the things that whatever we are discussing over here and all. And from tomorrow's lecture onwards, the actual the details of architecture that starts. Like first thing is the instruction set architecture that will introduce tomorrow, and maybe it may go for three lectures around that, 3 to 4 lectures, and after that we'll go for arithmetic units and on how to design that. Later on, the processor and so on. That way we'll move on. Okay, so before going to that, yeah, any
Sir,
questions?
actually, yes, sir, I actually faced some issues. So
Uh-huh.
I got 10 emails from the ERP, five of them saying that my course has been approved, and five of them saying that it is not approved. So,
Okay, so
sir,
no, no. You see that I have not approved the students. Yeah, some of them. Yeah, because you may be registered for twice, maybe for elective and for additional also, maybe.
no, sir,
Okay.
no, sir, only for
No, no.
additional.
There are no, no. I'm just listen to me. There are such cases were there in requesting for approval. Yeah, same student asked for approval for the same subject in a two like one as additional, another as project. One as additional, other as elective, something like that. I just saw that there are about 8 9 cases like that. In that, I just approved one of them, like additional. I have not approved any for anything for a project and all. I have approved only for additional and or otherwise elective. That is the way I have approved. And I have rejected I have not yet approved for candidates whose CGPA was less than 7.5. That is also there. So I don't know about your case and also once time approved, one time declined means the reason may be that. So there, I told you know, like the same candidate has applied for twice. Twice means maybe the two entities were there, two entries were there with the same name, same role ID. Everything is same, but one time he has requested for elective, another time he has requested for project. So such cases I have done that. Anyway, the otherwise you just check with me later on. Okay, if whatever the problem and all.
Okay, sir.
Is it clear? I don't know.
Yes,
Or
yes.
otherwise, you just send an email like whatever, just to me, just mention clearly about what is the case and all. Then I will see that from my role list and other things. Okay. Yeah. Okay. So, so just continue this introduction, and so in the last class we had discussed about like the some yeah, 8 the fundamental ideas that were used by the architects from beginning to even now also, and so those discussions we had. And after that, we discussed about the abstraction related to the programming or like software part, like from application software to coming to the machine language. What are the various abstraction layers and all? So those aspects we discussed, and then today just and when you look at the overall the basic components or basic blocks in a computer and all, so you can able to see that this particular diagram where it illustrates the same diagram you can able to see across the chapters. For every chapter, this will be like a kind of icon it used to be there. And if you look at here in this, there are like 5 components were there. You can 5 labels were there. You can able to see that. So one is the input and the other one is the output. And this input and output, as all of you familiar, like just inputting the data to a system, and you can see the outcome, the results or whatever. Sometimes over a display you can able to see the outcome, and sometimes over the voice speakers you can able to get the output, and sometimes the other way, like in the stored in a memory and all. So that way the input and output will be there. There are the two components. Like input, there are devices like kind of a keyboard, and there are the mouse, and there are other inputs, like sometimes even the drives, whatever the pen drives, whatever you are giving, that also can be used as input. And output will be like a kind of a display, or sometimes the speaker, and sometimes even the DVDs, whatever we can, CDs, whatever you can write into that. So that also can be used as input output peripherals. And then you have a memory, where this memory is actually connected, or the processor used to interact with the memory and all, whatever the execution unit used to be there. So that will be basically interact with the memory. And whatever the input and output, they are like deals with the memory, and they cannot directly contact with the in contact with the processor and all. Like we have a memory. And then coming to the processor, in that processor there are two entities basically. One is the controller, and other one is known to be data path. And this data path is nothing but kind of the actual execution that is performed over the data. It's known to be data path, sequence of the executions that happens inside. It's known to be data path. And the controller used to control the data path and all, at what time what action has to be taken, or what kind of execution, or what kind of activity has to be taken place. So that will be controlled or signaled by the controller and all. So that way, so these are the five basic entities or blocks any computer that consists of. One is the processor. Inside there are two entities, like a data path and controller, and a memory, and you have input and output kind of a thing. So these will be there across all the whatever the type of a computer it will be. It may be for embedded device, or it may be like embedded systems, or like a desktop, or like a PC, or like servers. We have basically visualized the overall systems will be of these three categories earlier. So any of these category and all. So these five blocks will be present in different ways. And so these are the like input output there. I have already mentioned that there are various things like input interface, out so storage devices, and so on. Anyway, you can it's a clear and all. There is nothing special in that to explain here. And then coming to the actual thing, suppose if you just try to look at the hardware components that are inside the system. So here this is the Apple iPad 2, where here you can able to see that there are different components were labeled over here. This is the display, LCD display, like with the touch screen, and these are the battery units. And so this is the actual board, computer board, where the main components will be there, will present on this board and all. And this is the zoomed version of that board. You can able to see here L-shaped board, and where here you can see the components that are like highlighted here. So A5 is the actual processor inside the Apple iPad. This is the main processor. It's a dual core processor with 1 gigahertz clock and all. You can see here A5 processor. And then to the left of this, you can have this one. This is known to be a flash memory, which is highlighted over here. And there is empty slot, that is also a flash memory slot. But suppose you want to enhance the memory size of flash memory. So this is a 32 GB, and you can have a provision for placing another 32 GB flash memory over here. And you have the power controllers over here to the right side, and then the IO controllers. So these are the like the actual board, the computer board, where the processor and all, even the memory, all these things will be laid over this. And so then coming to the, yeah, this was the like the processor, A5 processor and all. As I mentioned, it's a dual core, two core processor, and these are the data paths corresponds to that, and these are the various interfaces like IO. And then if you see that at the bottom, it is interface to the main memory, and the other static memories and all. And yeah, then coming to the inside the processor, as we already mentioned, that data path contains data path and a control. And the data path is nothing but which used to perform various operations on the data. Like basically the data path, you can see that in the later chapters, it will be, when you go through that, it will be, you'll get a more clarity on that. Data path means actually to when you perform the different operations and all, what are the different components that like that share that or that will be participate into that can be viewed as a data path. So basically in the processor, you can say that there will be like ALU, known to be arithmetic and logical unit and all. So which used to perform these basic operations like arithmetic operations and logical and so on. And then it used to perform the operations on the data, but the data inside the processor used to be there in the registers and all. So likewise, when you say the data path, it takes care of all of them, like including the ALU, then set of registers and other components that participate the execution of data and all. Then controller is nothing but actually here, as I mentioned, that we have a different, the data will be can be can be done. The different operations will be performed on the data at different points of time, and those things will be controlled by the controller by providing appropriate signals to the components at a different times. Different components will be activated with the different operations will take place. Suppose, for example, like accessing the memory and reading a data from a memory and all, then storing the data into memory or reading a data from registers, storing into the registers, performing operation of this one on the in the ALU or on the two data items, like performing addition, subtraction or something. So like all these things here will be part of the data path. And then whereas the controller and also it used to like activate these data paths at different times to perform the different operations on the data and all. So therefore basically the controller consists of these two things, like a data path and a controller. We'll see these details and very clearly when you are discussing about the processor and all. So that will be later, after maybe like after 2 3 weeks we have a discussion over the processor. How do we design the processor? What are the data path and what are the different entities in that? All those things we'll try to discuss that. So controller is basically the which used to control the data path. Like data path means like different entities that participate in the execution of the instruction and all. Like it may be memory, it may be like registers, or it may be the ALU, or it may be some other thing. Like then a cache memory, that also nowadays actually the processors itself inside the processor itself contains the memory, a small amount of a memory. So with that, the performance of the overall system will be improved and all. Like actually the processor which contains a set of registers and all, very small number of limited number of registers. But to enhance the performance along with the register set, if you have a memory which is which can be accessed at very faster rate compared to the main memory and all. So in that case, this is known to be cache memory, which used to be there sometimes within a processor itself. A small amount of memory will be there. It's known to be static memory. It's a very fast, that may very small in size and faster, like you can access it faster. Right? Mm, then the next thing related to the computers will be like when you try to analyze the performance of the system and the execution of instructions and all. So they depend upon the clock, system clock, CPU clock and all. So here the clock means because all the devices, whatever, all the hardware components, whatever that will be there as a part of the processor and other things. So they are the digital hardware. So they will be governed or they will be like operated in synchronization with a clock and all. So, and when you're dealing with the clock, suppose this is a clock representation, and here this is a clock period. And so during the clock period, the activity will takes place. And also in this one clock period, sometimes the data transfer takes place. Sometimes some operation will be taking place. So that way, the data transfer or a computation that happens in terms of a clock periods and all. Within a clock, some activity will happen and all. And sometimes no, at the transition times, some the state of the some components will be changed and all. Like we'll see that what is meant by the state of the system and all. At that time, we'll discuss about what is the state change and all. Yeah. And coming to the clock, there are two things. One is that what is the duration of the clock period, one cycle, what is the time, what is the period of, what is the clock period, and then the clock frequency. It means that how many these cycles will be there in 1 second and all. So this is example, you can say the clock period means we can say the 250 picoseconds, for example. So it means 250 into 10 power minus 12. It's nothing but 0.25 nanoseconds. It's a clock period and all. So for this, if you want to like see in terms of clock rate, how many cycles were there for 1 second means take reciprocal of this, it gives you 4 gigahertz and all. Like just simply taking the clock period, 1 over the clock period give you the clock frequency. So it means that there are this many clock cycles will be there in 1 second, like 4 gigahertz. Suppose, for example, in a one clock period, if you can able to execute one instruction, so what it means is that with a 4 gigahertz clock, the system can able to perform, can able to execute like this many, like 4 giga like instructions, like 4 into 10 power 9 instructions per second can be executed and all. So this is the clock frequency and clock period. Clock period is nothing but duration of one cycle, and the clock frequency is nothing but like number of cycles, clock cycles in 1 second. This is the terminology, simple terminology. Then coming to the like when you are you have a system, for example, computer, and then if you want to measure the performance of a system, one way, there are different ways you can able to measure. One way to measure the performance is that suppose if you give a task and a task is nothing but in the form of instruction sequence of instructions, then what it will do, then the CPU will execute these instructions one after another, and all. So for execution of each instruction takes certain number of clock cycles and all, right? So that way you can able to say that when you give a task and when you're after some time when it completes, then we'll say that when you analyze the performance of a processor or the system and all, you can say that how much time the CPU has taken for completing that particular process and all. So for that, the way is that it's nothing but CPU time. It's nothing but maybe 6 seconds or 10 seconds or 8 seconds or whatever. It may be order of milliseconds also. So how do you evaluate that? CPU time is nothing but how much clock cycles the CPU has taken for completing that particular task. The task is nothing but set of instructions. Suppose you have 100 instructions are there. So for completing those 100 instructions, how many clock cycles the CPU has spent? Like about 350 cycles or like whatever. So that way, this is a CPU. So CPU time can be computed like CPU clock cycles multiplied by like what is the time for each clock cycle, and it's nothing but clock period, right? So and this you can able to write in other way that a clock period is nothing but you can write a clock period as like 1 over the clock rate and all. 1 over the clock rate. Clock rate, as I mentioned, that it's nothing but the number of cycles per second and all. Number of cycles per second. So here I'm writing here this we are writing clock cycle time as 1 over the clock rate. So therefore the CPU time can be written as CPU cycles divided by clock rate. So if you want to enhance the CPU performance, or if you want to enhance the performance, it means that our goal is to reduce the CPU time. So how do you reduce the CPU time? Either by reducing the cycles in the numerator or by increasing the clock rate and all. If you increase the clock rate, or either by reducing the cycles. So either way you can able to enhance the performance. We'll see that what are the various implications on that. So yeah, there will be trade-off in this again, the clock rate versus this one when you are choosing the specific clock and so on. Yeah, here just this is simple numerical example. You can go through and need not explain this just to see that. Suppose we have two computers like computer A and computer B. For example, computer A is operating with a clock of 2 gigahertz. It's a clock rate. And then suppose for performing a particular task, this particular computer will take 10 seconds CPU time. 10 seconds CPU time. And for example, if you want to design another computer B, where if you want to perform the same task, whatever I mentioned earlier, it has to take, suppose if you want to, if you wish to take 6 seconds, then what will be the clock rate and all? That means how far, what will be the clock rate of this computer B such that it can able to compute the same task in 6 seconds and all. So for doing that, assuming that for performing this task in 6 seconds, so this computer B, it may need the number of clock cycles maybe 20% more than the computer A and all, computer A. So what here is given is that the computer A has 2 gigahertz clock, and then it take for computing a particular task, it take about 10 seconds of CPU time. Right? And if we want to design a computer B with a faster clock, where we have to finish the task in 6 seconds and all. And then assuming that actually here, suppose for performing this, completing the task in 6 seconds, the computer B will take the number of like CPU cycles that are required for a computer B will be 1.2 times the CPU cycles of this one, like the task A, the computer A. And so then if you want to compute that one, just try to see that the clock rate, we want to compute the clock rate. What is the clock that is required to finish the task in 6 seconds and all. So clock rate is nothing but, as per the earlier thing formulation, the clock cycles that are required for a B, computer B, divided by the CPU time of B, divided by the CPU time of B. This one, just this is nothing but just the previous thing, just this particular relation. From this, we want the clock rate of B. So if you take a clock rate here, then the CPU time will come as will be follows the denominator and all. And when you do that, the number of clock cycles of B is nothing but 1.2 times the clock cycles of A. So 1.2 times of clock cycles of A, and the CPU time of B that is required is 6 seconds. Okay. And now here, for knowing the clock rate of B, here the unknown is that the clock cycles of A. So the clock cycles of A now you can able to compute, because we know that the CPU time is 10 seconds for a computer A, and the clock rate is 2 gigahertz. So with that you can able to compute the number of the clock cycles for a computer A to finish the task, like this way, CPU time multiplied by clock rate. This is our 20 into 10 power 9 clock cycles, right? And now this is the clock cycles of A. So now you just substitute over here. So with that you can able to get clock rate equals to 4 gigahertz, right? So this is very just for simple illustration, like if you want to enhance the performance, then what way you can able to do? One way is that you can increase the clock rate and all, right? As you increase the clock rate, yeah, overall actually the number of clock cycles also will increase, because if you increase the clock rate means the cycle period the cycle period will be reduced. So therefore you need the more number of cycles and all. And the another way of analyzing the clock cycles will be, suppose when you say that on a computer A it takes this many CPU cycles and all, right? So it means that that depends upon basically the number of CPU cycles for performing a task, that depends upon the number of instructions that to be executed and all. The number of instructions that has to be executed. Right? Suppose you have a task that need to be performed. For the task, you will write an application software that is in high-level language and all. That's not an instruction count. And that instruction count, that is for each instruction execution, that is the like that. Those are the high-level language program, the commands, number of commands and all. Again, that will be translated into the machine instructions and all. So finally, for every program, it will be derived. It will be translated into the machine instructions. And finally, whatever the task is there, that task will be translated to machine instructions. Now we have a list of machine instructions and all, right? So the CPU time or the number of clock cycles is nothing but, for example, if you want to execute a particular task, first of all, we need to find out like how many instructions are required for performing that particular task. That is instruction count, right? And then once you know the number of instructions, we know that we can, for computing the number of CPU cycles, it's nothing but how many cycles are required for executing one instruction and all. For executing one instruction. So that way, The number of CPU cycles can be evaluated by using instruction count multiplied by cycles per instruction, right? It's a very straightforward thing, right? The instruction count is nothing but to perform a particular task. That task will be represented by a sequence of certain instructions, number of instructions. And then each instruction will require certain number of cycles and all. So therefore, the CPU cycles is nothing but total number of CPU cycles for performing the task is nothing but instruction count multiplied by the cycles per instruction, right? And again, this is just follow up of this one. The CPU time is nothing but number of CPU cycles. Number of CPU cycles multiplied by a cycle period or a cycle time. So that's what here the CPU cycles. Here you are saying CPU time. So CPU time is nothing but CPU cycles multiplied by time for one cycle, time for one clock cycle and all. So the same thing, and then we are writing the one clock cycle. The clock cycle time can be written as 1 over the clock rate. So this way you can able to compute the CPU time and all, right? And from this again you can say that the CPU time or the performance of a system can depends upon these three things. Either can be reduced because ultimately we want that less CPU time, right? So the instruction count can be minimized, optimized, or the cycles per instruction can be reduced or decreased, or the clock rate can be enhanced, can be increased. So either way you can able to, these are the three things that contribute to the CPU time. So therefore, if you wish to optimize the CPU time or minimize the CPU time, then these are the various things that can be performed, like instruction count, the cycles per instruction, and a clock rate and all. So yeah, that instruction count that depends on all the things like whatever, because we have application program. First we write by a programmer and all, and then that application program will be translated to a machine code using a compiler and all. And then the machine code is nothing but actually the instruction set architecture. That based on instruction set architecture, the compiler will translate the high level language code to the machine code. So therefore, the instruction count will be influenced by all these three entities and all, like determined by the program, the high level language program, and then the ISA, instruction set architecture, and as well the compiler also. If you have a very effective compiler and all, then it can able to translate the high level language into like some optimal number of instructions and all. That depends upon how good the compiler will be, right? Okay. Then sometimes no, like for carrying out instruction, different instructions will take a different amounts of time to compute, to execute that instruction and all. Sometimes they have some simple instructions which may take only one cycle of time to complete, and some instructions may take more number of cycles and all. So therefore, when you try to analyze that CPI, that is a clocks per instruction or cycles per instruction, so that depending upon the nature of instructions and all. If you have simple instructions, that will take less number of clocks, less number of cycles and all. If it's a complex instruction, it takes more cycles and all. So therefore, when you try to analyze the CPI, it is like the average across all the instruction types, various instructions. So that way it is determined by the, like, it's like average CPI will be based on instruction mix and all. Instruction mix means, as I mentioned, the instruction set architecture may contains some set of simple instructions. Some of them are the moderate complexity, and some may have the a complexity and all. And the overall the instruction the time or the cycles per instruction, that depends upon like the frequency of occurrence of these instructions and all. How many of them simple instructions used to be there in the normal programs and all. How many complex instructions will be there. So based on that, the average cycles per instruction depends on. Right. Yeah. This is again another numerical example and all. I may not. Yeah, please go through that. It's very simple. Like this, just to indicate that there are two computers with the different clock cycle times and different CPI, cycles per instruction and all. So in that case, just to analyze that, which of them will be the faster and all. Just by using the formulations, whatever we discussed, if you just plug in over here, you can come to know that which one is faster and all. Right here, if you look at here, see that cycle time of 250 picoseconds, other one is 500 picoseconds. It means that the clock rates are like double, like compared to suppose A is A has double the clock rate of B because the clock period of B is twice of A. So therefore, obviously, that is number of cycles will be more per unit time in case of A. And but here, if you look at the CPI, clocks per instruction or cycles per instruction, it is higher for the less clock period or higher clock rates and all. And this is lower for the lower clock rates and all. So then if you properly plug into that one, then we'll come to know that finally which one is faster and how much and all. Right? Then the next one is that this is just continuation of the previous one. As I mentioned, like the instructions, like it's not that all the instructions will take the same number of clock cycles and all. That depending upon the nature of instruction, some instructions, suppose for example, the instruction that deals with within the processor, for example, which has to deal with the contents of register, which are housed inside inside the processor itself. So in that case, just in within the instruction itself, that means within the cycle itself, in one cycle itself, the system, the processor can able to perform such execute those instructions and all, like which can access the contents of register, perform the operation, and then the output will be ready in the one cycle itself. Suppose if you want to access the fetch the data from a memory, for example, which is outside the processor, so those instructions will take more time and all because they have to access the memory, they have to send the address, they have to fetch the contents. So that way it takes more time and all. So therefore, when you're analyzing the clock cycles per instruction, that depends upon the nature of the instruction and all. So here just given the explanation related to that. So the clock cycles per instruction, the number of clock cycles for a particular program, that depends upon if you the whatever the how many types of instructions we have used, how many classes of instructions we have used. Suppose we have n classes of instructions, and for each class, how many instructions of such class will be there, and how many cycles are required for executing the instructions of that class. As I mentioned, like the instruction of a very simple nature, where it may execute the entire instruction in one cycle itself. There are certain instructions which can take about 5 cycles. Certain instructions they can take about order of tens, like 40 cycles, 50 cycles, and all. So if you want to compute the total number of CPU cycles or total number of clock cycles for execution of the program, depends upon this one, like how many instructions are there in a particular type of class. So that gives you the instruction count with respect to class I. And then we know that for execution of instruction of that class I, these many cycles are required, CPI, subscript I and all. And then with that, when you try to find out the product of the summation gives you the total number of clock cycles and all. The same thing here, the weighted average also, it's nothing but the same thing, except here, like we are dividing with the instruction count and all. Here, this is the total number of clock cycles, and we want that the average cycles per instruction and all. And we know that the instructions are not same, all they are from different classes and all. So therefore, we have to take the weighted average, the same thing, like number of clock cycles divided by the instruction count, total instructions. That gives you the total average number of clock cycles per instruction. Yeah, this problem is just related to that. Just to interpret that one, you have a different. You can see this one. We have a different classes of instructions here. For example, A, B, C. There are 3 classes of instructions and all. And for execution of each class of instruction, this many clock cycles. Like for A, it takes 1 cycle. For B, for an instruction of type B, it takes 2 cycles, and then C, so on. Right. And now, for example, you have a task, you have application program, and now the compiler used to translate that application program into the machine level instructions, some machine instructions and all, right? And if you use the different types of compilers, some compilers will use when you give when you use a particular compiler, it may generate a particular sequence of instructions based on the instruction set architecture. If you use some other compiler, maybe some other compiler, then it may derive some other sequence of instructions corresponds to that particular instruction architecture and all. And now if you try to analyze that actually, which one is the better, like because there are 2 sequence of instructions are derived for the same application program and all. And now if you want to analyze that, So which one is optimal, which one is better and all. So then by using this, you can able to, using this numerical, you can able to analyze that, right? It's a just very straightforward calculations and all. From this, you can see that the sequence one contains the, like an average, it takes the more number of cycles compared to the sequence two and all. Yeah, I can see that it's nothing like this. These numericals are used to give more clarity on the this one, like the performance calculations and all. And this is the overall formulation for a CPU time, like the overall formulation, like CPU time that is required to perform a particular task is nothing but the instructions per program, right? Because for every program we have some set of instructions per program multiplied by, like, cycles per instruction, because there are so many instructions were there corresponds to one program. And for evaluating, for execution of this instruction, how many cycles are required, this is the second factor, that is the cycles per instruction, right? So this gives you the first two factors, these two fractions, these two give you the multiplication of these two give you the total number of CPU cycles and all. And if you want to have CPU time, the CPU cycles multiplied by a clock period. So this is the clock period and all, 1 by clock cycle time. So this is the clock period, that is the cycle time and all. The cycle time is nothing but this one. So this way you can able to come. Yeah. No, this seconds is the time. This second is the time. Time is the final units and all. That is nothing but number of cycles per second, or like in 1 second. Yeah, number of cycles per second, right? Number of cycles per second, and clock period is nothing but the inverse of that, right? The rate, right? So that gives you this. This is nothing but the earlier we have seen in the formula, the denominator part, like in the denominator we have clock rate is there, no? So that clock rate is nothing but in the denominator, if you see clock rate is nothing but clock cycles per second, right? So since it is denominator, so it will be like this way, like seconds per clock cycle and all. It's nothing but clock period, seconds per clock cycle. One cycle, what is the time period for the cycle and all? That's nothing but seconds per clock cycle. As simple as that. Right. So this is the global formula, overall formula for computing the CPU time and all. Right. And then you see that what for in this CPU time, it consists of various components and all. And now can able to analyze that actually. We have seen that the application program. So above the application program, we have an algorithm which is close to the thought process and all. And then the programming language, high level language, which translates algorithm into sequence of commands in the high level specific high level language. And then the compiler, which used to translate these high level language commands to the basic instructions, which can be implemented by executed by the processor and all. And those instructions are part of the instruction set architecture and all. So if you analyze that, these things like all four will contribute to this IC. That is, what is that? IC means instruction count. Yeah, IC means instruction count. That is the number of instructions per program, and then the CPI, like obviously, and then the instruction set architecture, which influences the clock period also, because here the instruction set architecture means it contains the overall instructions. It's not just limited to this particular program and all. Instruction set architecture means the set of all instructions where the underlying hardware can able to execute, right? So when you are this instruction set based on this instruction set architecture, that influences basically the clock period and all, because based on the instruction set architecture, that means the types of instructions that contains in the architecture. So with that, you can able to design the appropriate clock period and all. If we choose very small clock period and all, then you need to have multiple cycles are required, and then the clock rate increases, then again that leads to a problem. Like at the same time, if you if you increase the clock period and all, it means the clock rate will come down. But if you increase the clock period, then what happens? There are some simple instructions which will take less than a clock period and all, because it may take about 5 nanoseconds if you keep the clock period as, for example, 20 nanoseconds to accommodate the some other moderate instructions, for example. Then these simple instructions can be executed only in 5 nanoseconds. Remaining 15 nanoseconds and all, even though it completes, it just wait for the next instruction to be executed. So therefore, the instruction set architecture will influence the clock period and all based on the types of instructions that it contains. So based on that, it has to the proper appropriate clock has to be chosen and all. Right. So these are the various factors that influence the various the parameters, various components that are involved in the CPU, contribute to the CPU time and all. Right. So therefore, ultimately, we want to have an efficient system. That means less CPU time. So therefore, in that, if you want to have a less CPU time, so these are the various instances where you can able to optimize that. If you write at a software level, you can have it at different places. You can able to optimize where you can able to reduce the CPU time, and similarly at the hardware level also. At the hardware level, by keeping a clock and by using the appropriate devices and all, you can reduce the time, overall time. Yeah. And yeah, these things we discussed about, like when you analyze the performance, as I mentioned, that the performance that depends upon the system which you are evaluating and all. Sometimes for certain systems, the response time is important. It's basically applicable for the personal computers or the systems with the single user systems and all. So there, the response time is very important and all, right? For example, when you're using mobile phones or or using a personal computer, desktop or laptop, whatever. So it's mostly interacted by single user and all. So there, the response time is very important, right? So whereas if the system is like if you have a server like which used to cater the multiple clients and all, so in that case the throughput is important instead of the individual response times and all. So that means the total work done are like a number of users or number of tasks that are completed in unit time. So that is important in case of the servers and other systems and all. So so if you want to reduce the response time and also what are the various things that can be response time is basically it's nothing but the CPU time, right? CPU execution time. It's not the only CPU execution time. There are a lot of other delays will be there. We'll discuss that later and all. But as of now, for the things to be make it simpler, assume that if you give a task, only the CPU acts on that. And if you can able to reduce the CPU cycles or CPU time, then the response time will be reduced. So for doing that, if you take the different options kind of a thing, for example, replace a processor with a faster version, then definitely like the response time will be improved, right? Or reduced. Or suppose if you add a more number of processors, for example, then of the same type, then the response time will not change if it is a single user case. But on the whole, if you had a multiple processors and all, then the throughput will be increased. And you suppose if you perform the multitasking environment, so in that case also, the things will be improved if you use the multiple processors and all. Because otherwise, if it is a single tasking system and all, then even though if you use a multiple process and all, then it may not be. But otherwise, if you have a multiple process where if you have a multitasking system and all, so in that case, obviously, if you have more process and all, then even the response time also reduced. But otherwise, what happens? Suppose if you're giving a task to a multitasking system, and where there are so many requests are already pending, and you are also waiting in the queue. So instead, if you have a multiple processes are there, then these clients will be given, these individual clients requests will be given to the multiple process so that your response time is also reduced, right? Yeah, there's nothing but here, it's not only the actual CPU time, the waiting time also will be counted here. And in that case, by having a multiple process and all, that waiting time can be reduced. With that, the overall response time also can be improved. Yeah, anyway, this depends upon the scenario where what we are where we are using and what system we are using, what application we are running. So all these things also matters. The next one is that this is one more thing, as we have seen that in the when you are analyzing the CPU time and all. So the CPU time, as you have analyzed, either it's nothing but we had to either reduce the instruction count, or we can also increase the CPU time, or can reduce the CPU time by increasing the clock. Increasing the clock means the clock period will be reduced. So therefore, the overall time, the CPU time that takes for execution of a task also will be reduced. So with that, actually, so over the generations, over a period of a time, the clock period is reduced, or nothing but the clock rate has been increased, right? Like year by year, version by version and all. And so when the clock rate is increased, you can increase the clock rate. So with that, the CPU time will be decreasing and all. But you can increase the clock rate to a certain rate, certain limit, because as you increase the clock rate, then what happens? It influences the power drawn by the system and all, or the power that will be dissipated by the system is also increases. So as the power increases, we have a problem. That means well, as the power increase, it should be then they generates the heat, and also we had to have proper cooling mechanism. And so that way there will be a limit to increase the frequency and all. So as you increase the frequency, obviously the CPU time will be reduced, but you cannot increase the clock rate beyond the time because of this power. That means when you reach the power to a certain level, it leads to the heating the devices, and we should have proper appropriate cooling mechanisms has to be required. But here, if you look at here, but if you look at the increasing the clock rate versus the increasing the power, so it's not proportional. Because as a clock rate increases, here it starts from like a 10 and it's maybe lesser than that one. And approximately clock rate increases in the terms of like hundreds or thousands. But if you look at the power is varying from 3 volts, 3 watts to maybe it go up to 100 watts and all. That means the power has been increased to 30 times for raising the clock to almost like hundreds or 300, like around here 500 times around that time. But the power has been raised to only 30 times. The reason for that is here, if you look at here, the power dissipation will be like capacity load multiplied by voltage square into frequency. As you increase the frequency, obviously power increases. But what is happening here is that to control the power, the people now the chip manufacturers and other things, they reduce the voltage and all. Earlier it will be started with 5 volts. Now each time when you raise the clock, they also reduce the voltage and all. So with that, the power is not increasing proportional to the clock rates. So that is the reason that actually even the clock rates has been raised to order of hundreds, but the power has been raised to 30 times. But here again, it reaches to a saturation limit where you don't have a sufficient cooling mechanism. So therefore, here you cannot increase the clock rate further. The reason is that we already decreased the voltage from 5 volts to 1 volt. Right? Earlier we have 5 volts, then it has been slowly reduced by zero point 0.5, zero point 0.5, so on. We reduced to 1 volt. And here, if you reduce further, then again there is a problem of leakage. There is a power leakage will be there, and again that is a problem and all. So therefore you cannot reduce the voltage still further. That is the reason that you cannot raise the clocks further. So this is known to be a power wall. There's a problem for raising the clock rate beyond this limit, because we reduce the voltages to some extent 1 volt. Beyond that, if you reduce, then the leakage power will dominate, will increase, and again you have a leads into problem, erroneous thing. So to overcome that, people thought about, instead of increasing the clock rate, where they can able to support by stabilizing the clock rate by increasing the number of processors and all. You can see that after this, we have still that we have only the single core processor, Pentium, then afterwards they have a core 2, core 4, core 5, and so on. Like the number of processors have been increased. So with that, the performance can be enhanced and all. So, and this is the problem just related to how to reduce the power and all. For example, if you reduce as per the formulation, the capacitor load, voltage, and frequency, if you reduce how much the power you can able to reduce and all. And the power wall, as I mentioned, that you cannot increase the frequency beyond a limit. You can increase it. We have increased up to like a certain limit and all. And with that increase, we subsidized by reducing the voltage and all. But we cannot reduce the voltage still further. So that's where the problem is that. So that's where we can overcome this problem by introducing the parallel processors, more processors, multiple number of processors and all. So that's what about the multi-processors and all. Yeah, here we'll stop over here and all because it's already 1 o'clock and all. So we'll stop here. Yeah, let's stop here. We'll continue this from tomorrow. Anyway, just we'll have only another 5 minutes of discussion over here and all. Yeah. Okay, we'll stop here. Then